Welcome to Who's in STEM. I'm Ken Ono, your host and STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics at UVA. Our goal is to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics. Today we're talking about amazing people. I think you all know what a Renaissance man is. A Renaissance man is a well-educated person who excels in a wide variety of fields. The term, as you probably know, is meant to describe great thinkers from the Renaissance period of history. Think of names like Machiavelli, Michelangelo, and Raphael. Now, a polymath, and I'm a mathematician, so I love the word polymath. Now, a polymath is a special kind of Renaissance man. You see, a polymath excels in a wide variety of fields by drawing on complicated bodies of knowledge to solve specific problems. A polymath, as the term might misleadingly suggest, doesn't have to be, but often is someone who is good at math. So think Leonardo da Vinci. Think Galileo Galilei. Today, and this isn't an exaggeration, today we're speaking with a UVA polymath who actually turns out to be a real live mathematician. So really like the ultimate in polymath. His research is making waves in a wide variety of fields in the world of data science. The complicated stuff he draws on are data sets about our own planet, planet Earth. These sets come in many forms, and they're super complicated data sets, and these are data sets that matter. His work is surely going to impact all of you who are listening to this show. What specific problems interest him? Well, he wants to detect terrorist activity. He wants to make predictions about erosion, assisting ecologists. He wants to offer advice for urban planners. He wants to combat food insecurity. And he wants to assist relief workers deploying aid and assistance in times of crisis. Think hurricanes. Think earthquakes. This is indeed a wide variety of problems. And he uses math, and so the name fits. Polymath. It's a pleasure to welcome Bill Basener, UVA Professor of Data Science. Bill, welcome to Who's in STEM.
Thank you, Ken. It's a pleasure to be here.
So, Bill, you study data sets. You're a data scientist. But what I'm really fascinated about are the data sets that you study. They're about our Earth, our planet, so everyone should care. Tell us, what kind of data sets do you study in some detail?
Most of the data sets I work with are collected with a process called remote sensing. So remote sensing is collecting information about an object with a sensor without making contact with the object. So for example, anytime you take a picture with your cell phone, that's a remote sensing activity. A lot of the data sets I work with are collected from overhead aircraft and satellites about the surface of the Earth. Your camera on your cell phone collects in 3 colors, which correspond to the 3 colors that our eyes see, red, green, and blue. But there's a lot more information out in wavelengths of light that our eyes don't see. So for example, satellites collecting in infrared will collect information about the temperature differences on the surface of the Earth. Security cameras in infrared can see things at nighttime.
So this is a whole lot like why we need many different kinds of telescopes for different wavelengths of light.
Exactly. A lot of this processes I use started in astrophysics, looking at objects that are very far away. One of the most interesting technologies is a field called hyperspectral imaging. So a hyperspectral imagery collects light in hundreds of wavelengths. So you can do actual spectroscopy about every pixel in the image and determine the chemicals that are present on the ground if the image is taken from, for example, a satellite or an aircraft.
Wait, so you're saying that from the images you collect, you could distinguish between a cornfield and, I don't know, a gravel pit?
Yes, exactly. You can distinguish between different things that look the same to our eyes. So you could tell the difference between powdered sugar and baby powder and, say, for example, anthrax. Another amazing technology that I enjoy working with is LiDAR. In LiDAR, we take measurements by shining a laser at an object, and we'll shoot out millions of laser pulses per minute and build a 3D model of objects from as far away as an aircraft looking to the ground or a satellite to the Earth.
What does LiDAR stand for? It's an acronym for something, right?
It stands for Light Detection and Ranging.
light detection and ranging. Thank you. And when was LiDAR invented?
20 or 30 years ago. A lot of these are gradual inventions over time. But it's the same technology. If you've ever used a tape measure at home and you measure the distance across the room, they have effectively tape measures that work by shining a laser across the room to make a measurement. It's the same technology as that, but at a much higher data rate.
So I imagine that many of these advances in technology have their origins in military applications.
Yes, that's correct. A lot of my early work in these technologies was up at RIT, which is in the Bausch & Lomb and Xerox hub in New York.
That's what, Rochester Institute of Technology?
Yes, that's Rochester Institute of Technology. Yep, exactly. And that area has a long history supporting government activities with satellite imagery, going back to the early Corona satellite days.
How do you use these data sets? So you're collecting data from satellites, you're collecting this LiDAR and this hyperspectral images. How do you use these data sets, and how do you apply the math to studying these data sets in the real world?
So these data sets, particularly hyperspectral imaging, can be phenomenally complicated. So if you imagine a satellite image of Charlottesville, and you imagine the information that's in there about every chemical that's visible from a satellite imagery, the road surfaces, the rooftops, the people, the cars. So it's a phenomenally complicated data source. So using these, it involves challenging math, which maybe we'll get a chance to talk about a little bit. So just some of the applications where I've used these, I worked with U.S. organizations locating IEDs, which are improvised explosive devices in Afghanistan and Iraq.
And those devices are small, right? They're like the size of a gym bag.
Correct, yeah.
So you can detect them from images taken 2 miles high?
Correct. So the object can be smaller than a single pixel because we're detecting the chemical bonds that are present rather than the shape of the object. And as long as we could determine the chemicals that were present in those IEDs, we could determine where the IEDs were. Other applications include counter-narcotics. So if we could determine what chemicals were being used in the narcotic activity, we could detect those from an aircraft or a satellite. More recently, I've been working with demining activities in Ukraine, which is landmines are a phenomenally bad problem in Ukraine. They get dispersed over farmers' fields, and now the farmers can't harvest their crops because of the mines that are present. And so we're working on developing methods to locate mines using hyperspectral imagery.
Wow. Do you have some images that have been taken over a long period of time so you could see, pinpoint exactly when these mines were planted?
There's data sources from satellite imagery, not with hyperspectral, but with an 8-band multispectral sensor that are collected by Planet Labs. And if you've heard of the constellation of small satellites that have gone up, they collect imagery over every location of the Earth a couple of times a week. So you can look back in time, and it's 3 meters square per pixel, and you can look back in time and see changes almost daily throughout history of certain locations. So you can see when things were changed on the Earth.
So I want to understand the hyperspectral imaging. So I imagine, and please correct me if I'm wrong, but I imagine what you're doing is you're collecting these images collected by satellite and doing the analog of what a mass spectrometer would do in your chemistry class. Would that be an accurate analogy?
That's exactly right. The light that hits an object, certain wavelengths will be absorbed into that object into the energy that's present in the chemical bond vibrations. So picture the chemical bond being a spring between two objects. If the light is at a wavelength that resonates with that bond, the energy will be transformed into vibrations in the bond. If it doesn't resonate, it'll be reflected back. So if we can locate the bands of light that are associated with certain bonds, we can locate certain materials on the ground.
So, Bill, the technology you use, honestly, it sounds amazing, right? It sounds like your big brother hovering over the Earth, and you can't hide, which is kind of a theme. Big data is coming after you, but it's all put to wonderful use here through your work. But I have to imagine this is a satellite is expensive, right? Tell us about the relative costs, and have you participated in the design of some of this technology?
So 20 years ago, to get a hyperspectral sensor, it would cost tens of millions, hundreds of millions of dollars, and the only place you could find was large organizations like NASA. Now these hyperspectral sensors and LiDAR, they're commercially available. This evening, in fact, I'm driving up to Boston to work with a company that I work with called Headwall, and they sell LiDAR together with hyperspectral on a UAV that's available not quite at the hobby price, but at the price that a reasonable scale farmer could purchase one and use it to monitor their crops. I'm also working with a company called Skyfi, and we're developing web interfaces so anybody anywhere in the world on your laptop or your phone could purchase satellite imagery or even task a satellite to collect imagery over a location that they're interested in. And it could be high resolution, or it could be SAR, synthetic aperture radar, another remote sensing technology we haven't talked about yet. Or it could be hyperspectral imaging over a location you care about so that you can use it to find things that are of interest to you.
So as I mentioned earlier, you're also known for your commitment to humanitarian efforts. I think I mentioned think hurricanes, think earthquakes. One of your efforts really stands out for me. It's the work that you did in the aftermath of the devastating 2010 Haiti earthquake, which was magnitude 7.0 on the Richter scale. How did you use big data? What did you do? What did you do to assist in the aftermath of the horrible earthquake?
That was a horrible tragedy, that crisis following the earthquake in Haiti. It left some 2 million people homeless, whose homes were destroyed by the earthquake. And what was going on there was a large number of international organizations coming in to provide relief. And they would provide blue tarps to the people whose homes were destroyed. And the people were making these small makeshift villages and using the blue tarps for shelter. But it was difficult for the relief workers to know where those villages were popping up in real time. And they needed to find them so that they could distribute food and water and healthcare and other aid to those people. So what we did at RIT, we worked with World Bank and other aid organizations. We would fly aircraft taking off from Puerto Rico, fly over Haiti and collect imagery and remote sensing data and land it back, send that imagery up to New York, and the software I wrote would scan that imagery and find those collections of blue tarps that were forming, indicating those makeshift villages. We would then produce Google Earth push pins, send those back to Haiti, and the next morning when the relief workers got up, they would have Google Earth push pins directing them to where the people were that needed help the most. Just the same way that you'd use Google Earth or a mapping program to find Starbucks, they could find the people that needed help.
Oh, that's amazing. And this made use of the hyperspectral imaging or the LiDAR or all of the above?
We flew multispectral imaging and LiDAR in that case. The U.S. Geological Survey used that LiDAR to assist them in understanding the earthquake and where the fault line was.
Oh, that's amazing. Just hearing you talk about your ability to discover small encampments of stranded people, to my mind, suggests that there should be many, many more applications. So what else does this sort of technology allow you to discover about planet Earth that would have otherwise been accessible? There are other examples that you could tell us about.
So one of the interesting areas I'm working on right now is understanding vegetation growth and processes using LiDAR and hyperspectral imaging. This is a collaboration with the Architecture School and the School of Data Science. We're working at Morven Farms to monitor vegetation growth and do experiments and then collect hyperspectral imaging with airborne sensors and ground spectrometers. And the goal there is if we can understand the ecology and what's going on, we can do a better job for urban planning. So if you're going to, for example, plan growth around the entire Chesapeake Bay region on a large scale, you want growth that's going to work with the natural systems that are present, not against them. Think green infrastructure, not concrete.
So, Bill, this technology is fascinating. I think we can all understand how extraordinary it is that you can learn more about planet Earth by viewing it from above than literally being on the ground, feet away from the things that you're trying to discover. So I have to wonder, Indiana Jones, right? Indiana Jones is looking for some lost city, right? I have to believe that sort of technology could be a useful tool for him and others in the field. Have you thought about that, or maybe some of your colleagues?
Yes, there were a number of instances where things would be found in the overhead imagery that we were looking at, and then the archaeologist on the ground would go there and find cities that nobody knew about. In fact, I had some graduate students who traveled to Central America to work with those efforts, finding lost cities.
Okay. Oh, that's incredible. So earlier, I also mentioned your work with regard to food insecurity. How does big data enter there?
That's a good question. So I have a graduate student, Captain Jade Preston. She's in the Air Force.
Captain. Oh, okay.
Yeah. Yeah, she's very accomplished. So the World Bank estimates that in Africa, 1 in 5 people go to bed hungry each night. And there's an estimated 140 million people in Africa who have severe food insecurity. And this crisis is expected to get worse with the war in Ukraine, disrupting the supply chain of food, both fertilizer and wheat that goes to feed a lot of the African countries. And so what we do is we're working with aid organizations who bring in food to support the people in Africa. One of the main problems is the locations where that food is needed fluctuates year to year depending on local crises, on climate variations. And so we have a data set that Jade's put together that involves demographic factors, the impact of food insecurity across different age levels and demographic groups through populations, and social stability, and supply chain networks across the continent. One of the remote sensing data sources that we have is NASA satellite imagery over all of Africa. So what we've done is looked back 20 years and in every month determined the amount of vegetation and its health in each pixel across the entire country, in each country in Africa. And so this gives us a historical relationship between the vegetation health and environmental fluctuations that are present in the NASA multispectral satellite imagery and the presence of food insecurity in those countries. So we're looking at that data, all of those data sources together to make predictions about which countries are most likely to have food insecurity each upcoming year, 1 year in advance.
And you can provide this information to the World Bank and relief organizations to help target the places that need the most assistance.
Yes, we're working with Save the Children, which is an international nonprofit aid organization. They're an incredible organization. They've been helping with every large-scale humanitarian crisis going back to World War I. And so they take food that's stored in Europe and they ship it to locations in Africa. But they need to know ahead of time where the food crises are going to be occurring so that they can ship it and get a storehouse filled in a warehouse ahead of time. And so we provide our predictions in a web interface that they can go use online to determine where the crises are most likely to occur.
Oh, Bill, this is great. So there's a common theme here, whether it's assisting after an earthquake or preparing for anticipated food insecurity needs. It's clear this work is so important. I want to shift gears here a bit. Bill, you've been in the news. It's been widely reported that you've been awarded a significant NSF grant to support your research on AI, artificial intelligence, with regard to threat detection. So congratulations. Tell us about it. What are you going to do?
Thank you, Ken. So this work is very exciting to me because it involves taking the latest advancements in AI, math, research, and technology and combining them with the latest research in the remote sensing technologies. What we're going to be doing is looking at objects in imagery and remote sensing data, and then using the AI to understand the context and the activity that's present in that data. For example, if you go into ChatGPT and tell it that you see a mineral called ulexite on the ground, it will give you a dozen or so different uses for ulexite, including new age psychic properties and other things. If you instead tell it you see ulexite on the ground and you're in California and there's a bulldozer nearby, it will tell you that ulexite is a mineral that contains borate. And what you're likely looking at is a borate mining facility, which it turns out to be correct. So what we're looking to do is to be able to combine different sources of information, historical activities together with observations from remote sensing to infer, in this case, in particular, threats.
Can you give us examples of the threats? Pretend I'm a senator. You're pitching me and I want to learn about your project. So what threats will the tools that you develop assist us in preparing for, detecting?
So there's a lot of cases where remote sensing gives us direct information about threats. So for example, when there's wildfires, the remote sensing can tell us where the hot spots in the fires are and where they're likely to spread.
So that's a real-time problem.
Yeah, exactly. So we can get real-time information about where the hot spot is in the fire.
And some other threats, right? I think threat, I think terrorist threat. I think the threat of another pandemic, these sorts of things.
So one of the critical questions before the war in Ukraine was whether Russian forces in Belarus were lining up for an exercise or to invade, right? So this technology could look at the formations that are in those forces and where they're deployed and how they're deployed and infer if those organizations of those deployments were indicators of an invasion or a practice exercise.
Uh-huh.
On the immediate scale, the tools that we're developing will be able to look at organizations of troops in the field like that and determine whether they're lining up to fire a barrage of artillery on a city or whether they're lining up for a movement or a storage activity.
Let's circle back to the math. You kind of made it a point at the outset of the episode that you're a polymath. So, as I said, I introduced you as a polymath. It's clear we've covered the poly part. Your work it spans so many different fields. But I want to talk just briefly about the math. And after all, I am a mathematician. So I looked this up. I checked out your CV. You wrote your PhD in topology and dynamical systems at Boston University, defended in 2001. And for the listeners out there, I can assure you this is very pure mathematics. Nothing related to earthquake relief, food insecurity, hyperspectral imaging and LIDAR. All of that begs the question, how did you evolve as a scientist? And maybe you could add to that, how do you use your mathematical training today in your work?
That's a very interesting question. So dynamical systems is a study of processes that change over time. Think you pull back a pendulum, you let go, it swings back and forth. That's a very regular change in the location of the pendulum over time.
Or a butterfly flaps its wings in South America and something horrible happens to the stock exchange.
That's exactly right. Yeah, those are the complicated versions where you can't write down equations that would tell you how to get from the butterfly's wings to the stock exchange. And so that's where topology comes into play. Topology is a field that was developed primarily by Poincaré, but over the past century or a little further, to understand dynamical systems that were too complicated to understand with explicit formulas. And so topology deals with complicated geometry in high dimensions and helps us to understand that complicated geometry.
Shapes and figures and configurations, that's what topology is about.
That's exactly right. So my early work in topology gave me a picture of the world where topology is useful for understanding the complex geometries that are too complex for explicit formulas. In data science, this topological perspective provides a way to deal with very complicated data sets and to get information out of them without having explicit formulas for what those solutions are ahead of time. So in a funny way, I'm still a mathematician. My passion is still about the mathematics and the core ideas that are here. And I still look at things the way a mathematician would, I'm sure, the way you...
Rigorously, right.
Rigorously, and I see beauty in those relationships, right? The same way a person looks at a sunset and says, that's beautiful. That's what gets me excited each morning, is seeing the beauty in the relationships that we can uncover.
Great. So, Bill, tell me a little bit about your childhood. On many of these episodes, I like to do somewhat of a deep dive into how our guests ended up getting into science.
So I was born in New Haven, Connecticut, when my father was a Gibbs professor at Yale.
Gibbs professors at Yale, they're mathematicians, so you're a son of a mathematician.
That's correct. And two of my children are mathematicians now, working for the U.S. government in different capacities. So my father, after working in academia for a little while, took a job with IBM and was working with computers. So the mathematics and computer connection was something I cared about early on in life. I started programming when I was about 8 years old. I was on a TI-99. I don't know if anybody still remembers these, but you would save your data on a cassette tape rather than a floppy disk.
Yeah, there was no cloud there. The clouds were things that were just in the sky.
It's
right?
Exactly right. And so the first program I wrote was a chat bot, so I could talk to my computer about my first and second grade teachers.
And did the teachers, did they participate? This kid, Bill,
The teachers didn't participate, but my chatbot turned out to be very sympathetic with me about my struggles with some of them.
Well, that's fascinating. You know, I like that you take inspiration from actual real-world events. You put the math, the data science, and the engineering to good use to make the world a better place. You're interested in assisting after crises. And, well, I'm wondering, last week, we all saw the horrific news out of Maui, where the historic Lahaina town was completely leveled by a firestorm. It was the perfect firestorm, as we've seen. It was a convergence of so many different factors. Severe drought, as we understand, was probably the result of climate change. Hurricane Dora to the south and a powerful high-pressure system from the north, all conspiring to whip up tremendous winds that fueled this storm. Can big data, can your work help make better predictions and possibly lead to interventions that can help urban planners who worry about the possibility of these horrible disasters?
Yes. So there's near real-time satellite imagery that collects data sets that will be helpful in understanding the vegetation conditions that would lead to natural fires or make forest fires a danger. There's also NASA satellite imagery that locates the hotspots in the fire. So as soon as they start, we can predict where they're going to spread and where crises are likely to occur. So, for example, when we have stressed vegetation that has less chlorophyll and less water content, these satellites will help us understand where there's a danger of a forest fire if it occurs.
And the real-time part is really important, as we've now learned from the news reports. This fire at points was moving at a mile a minute. And so time was of the essence.
One of the things that really excites me about this field is the acceleration and availability of the technology and the data. So there are small CubeSats circling the Earth that can take images of locations on the Earth in near real time.
Yeah, so for the listeners, I can tell you that just the other day, Bill sent me an email with a photograph of one of these satellite images showing the fires in, I assume, real time. So I hope you and your colleagues participate perhaps in the aftermath and perhaps in providing assistance to public policy. This cannot happen again.
I agree.
So, Bill, you're a mathematician, but you're a professor of data science. The School of Data Science is a big thing here at the University of Virginia, and it's still in its infancy. It's growing at an extraordinary rate under the direction of my friend Phil Bourne. What's it like being part of an emerging school? You get to define what the School of Data Science will be here at UVA. You're part of a major effort. What's that like?
Oh, it's very exciting. It's an honor to work with a lot of the people of the School of Data Science. There's amazing people. The school is as you say, in its infancy. It's like working in a startup company.
And you don't even have a building yet. It's almost done.
Yeah, what you see going on the corner of Emmett Street and Ivy is a metaphor for what's going on inside of the School of Data Science, right? So we're standing up all these new people, all these new relationships and programs and looking for what we can do and developing something that's going to be really special, that's going to last a long time. And it's amazing to be able to be a part of that as we're building it from early on.
So for UVA students interested in your work or students who are thinking about coming to UVA, right, and who are interested in data science, what message do you have for them? How can they get involved?
So my first message is find what you're passionate about and find a way to connect with that. So hopefully...
And for you, that's everything.
For everything involving data and math, yes. There's a lot of information on the School of Data Science website about the exciting things going on in the School of Data Science. If you want particular information about what I'm doing, my UVA detailed website is at billbasener.com. So students are invited to come there, look at things, and if you find anything that interests you, send an email to me and we'll see what we can do together.
We've had on the show other folks in data science, and we plan to have more guests in the future. So the School of Data Science not only touches on some of the topics we've discussed, but it also has significant projects in health, significant projects in basically all of the sciences across the fields, in medicine, in sports analytics, and so it's been exciting to see this pop up and grow into what I think will be one of the best schools of data science in the country. So thank you, Bill. You're both a front-end and a back-end example of President Ryan's vision for UVA to be great and good in all that we do. Thank you for your dedication to UVA and for using your skills to make the world a better place. I'm Ken Ono, STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics, and you've been listening to Who's in STEM.
Who's in STEM is produced by Catherine Kossaboom, Ria Verma, Mary Gardner-McGee, and Ariane Ballou. Our music is composed and performed by Robert Schneider and John Ferguson of Apples in Stereo. Follow us on Facebook, Instagram, and Twitter. Listen and subscribe to Who's in STEM on Apple Podcasts, Spotify, or wherever you get your podcasts. We'll be back soon with another conversation about scientific and technological innovation at the university.